we're good. You guys got that? You guys can see here. Life is grand. Starting chapter 3 today. This is exciting. Alrighty. You've seen that picture before because you'll recall we did section 3.5 when we were doing limits. So obviously we're not going to do it again. We're going to skip that. But we are in chapter 3, which is applying derivatives. So today we are going to start talking about extrema, which you probably have no idea what that is, but that's my job to show you what extrema is. So we're going to talk about, oops, wrong way. Come on. There we go. Obviously understand the definition of extrema. We're going to talk about the difference between something called an absolute extrema versus a relative extrema. And we're going to talk about extrema on a closed interval, which means instead of the entire function just starting and stopping at certain points. And then, of course, you should be able to snap your fingers. Yes, everybody? Can anybody not snap their fingers? Okay. Dylan, you got it? Okay, good. Just checking. Okay, so let's start with this function. It is a cubic, and I'm going to ask a general question. And then as you answer the question, we're going to classify it as a silly response, an Algebra 1 response, or a calculus response. Okay? So for instance, what can you tell me about the graph is the question I'm asking. If you tell me something like it's red, that would fall into the category of a silly response. Okay. The other answers that you give will either be an Algebra 70 or a basic Algebra 1 response or a calculus response. Go. What do you got for me? Anything about this graph other than the fact that it's red because I gave you that already.
It's a cubic, correct?
Okay, so was that you?
No, I said
No.
that.
Marcus just said it's a cubic. Good. Okay. It goes like this, and it says at the bottom there that it's a cubic. All right, what else? That would be an Algebra 1 statement.
Its derivative would be
Wait.
quadratic.
Hold on. You wait 1 second. What did you say, Prasad?
Its derivative would be a quadratic.
Excellent. That would be a calculus response there because we've talked about how the degree of an equation drops by 1 every time you take the derivative. So the derivative of that cubic function would be a quadratic, and then you take the derivative again, and you get a linear term, then you go to a constant, then you go to 0. Good. What'd you say, Max?
It has 2 horizontal tangent lines.
Okay, so did you guys all hear him? Could you hear that? Okay, he said it has 2 horizontal tangent lines. Where would those be, Max?
I don't know the exact points, but like at the top of the first arch, and then like, yeah, there, and then at the bottom of the second verse.
Good. We call that a hill and a valley, or a peak and a valley. Okay. Good. Go.
It has 2 vertical asymptotes, right?
Nope.
No?
Nope. What can you tell me about the tangent line in that region of the graph?
It has a negative slope.
Positive slope, but yeah, you're on the right track.
Oh, a positive.
Right.
Yeah.
Okay, I knew that's what you meant. Which would also be true over here. So part of the graph, the tangent will be positive. Part of the graph, the tangent will be negative. Okay. What we're going to focus on today is what Max told us, and these spots where the tangent lines have a slope of 0. Okay. And those are what we call extrema. All right. Now, how do we know that? Well, let's do some calculus. What's f prime of x? I'm not going to waste your time by asking you, because I'm assuming you can all do this. We would get that. Okay. What I'm going to solve for now is I want to know where's the x value that this happens. Okay. I should get 2 answers. And we've done these types of problems before. We just didn't know why we were doing them. So we've done a lot of problems like where is the tangent to the graph Where does the tangent of the graph have a slope of 5? Where does the tangent of a graph have a slope of 0? Where does the tangent of a graph have a slope of -7? We're going to focus mainly on 0. So I'm going to take this and set it equal to 0 and solve. X squared is equal to 2/3, so x is equal to, don't forget the plus or minus. Okay. Somebody have a calculator? Max, you got a calculator handy there. Could you tell me what the square root of 2/3 is, please?
0.816.
Okay, so we just did the calculus and we found out that those horizontal tangent lines should happen at 0.816, which is exactly, well, not, it's pretty good compared to what we see on the graph. So that would be 1, this would be -1, so it's a little bit before -1 and a little bit before 1. Okay. That's the gist of what we're going to do. In fact, we've already started doing it. But we got to get some terminology under control first. Any questions on this before I move on? Good?
Why did you set the y equal to 0?
Because that's where the tangent line, remember the derivative is the slope of the tangent line? We want the tangent line slope to be 0
Oh, okay.
because it's horizontal.
Oh, got it.
Okay. All right, everybody else good? And away we go. Okay, so we're going to start with something called an absolute max or min or a global max or min. They mean the same thing. I don't know why the math world can't just pick a name and go with it. I will most commonly call it an absolute, but occasionally somebody will throw a global in there. This probably makes no sense to you whatsoever. And we can go through the analysis of the calculus speak, but I do have it in English for you. If you look at the entire graph, or if you look at an interval, what's the highest point on the graph? What's the lowest point on the graph? Okay, and I know you're writing, bear with me, because I want to be able to show you a graphic of this. If I come back to this picture, and I look at the entire graph that I have here, where's the lowest point on the graph? Well, the smallest y value I'm going to find right here. That's obvious, which would be at -1.5, it looks like. That would be my absolute minimum. Now we talk about an absolute maximum. Well, where's the absolute maximum? It doesn't have one. And the reason it doesn't have one is because it's got that pesky little arrow there. And that little arrow means it keeps going on and on and on forever and ever and ever. When you're looking for an absolute max or an absolute min, you want a numerical value. And remember, we talked about most of the time infinity is not considered a number. Okay? Does that make sense? Yes? Okay, a couple head shakes. We're good here? So again, if you're still writing down, let me give you that again. Excuse me. Most of the time, in an absolute max or min problem, if I just give you the function, it's not going to have an answer. So a lot of times what we'll do is we'll restrict it to an interval. And we'll say, tell me where the absolute max is in this interval. Tell me where the absolute min is in this interval. What's the smallest value? What's the biggest value? And that's why they use this term I here, because they're talking about an interval. This will make more sense when you see my example that I have on the next slide. Okay, here's the process. Find the critical numbers. Well, we're going to have to talk a little bit about what a critical number is in a second. And then we're going to check the endpoints. This is the other thing to make sure. The endpoints would be the A and B term from the interval. And then it's real simple. The biggest value is the max. The smallest value is the min.
Should we write this down?
I wouldn't, but you can if you want. Okay, so what does this mean graphically? I'm going to go back to my example again, get this stuff out of the way. Now, instead of looking at the entire graph, I'm going to create an interval. And that interval will be given in the problem. So let's suppose I said, okay, I'd like to know the maximum and the minimum on this interval from here to here. Actually, let's go all the way to 0. It'll make it easier. I want to know the absolute max and the absolute min on this interval. And without getting into the numbers, we can see this would be the absolute min because it's the lowest point on the graph. And this would be the absolute max because it's the highest point on the graph. In that interval, okay, again, going from point A to point B. Does that make sense? Give me a thumbs up if that makes sense and we're good. Excellent. All right, we good here? All right. Let's look at an actual numerical example then. So I've got a graphical example here, which isn't that, I think does a good job of explaining what we're going to do, but when we have to actually calculate them, it gets a little nastier. Okay, so here's my function. I chose a quartic, which if you'll recall, quartics are either going a W going up or a W going down. This one happens to go up because it's positive. All of that is irrelevant. I also have an interval. Okay, so I need to do two things. I need to find the critical numbers, which I'll explain in a second, and then I need to test some points. Okay. So, what are the critical numbers? The critical numbers are where the derivative is equal to 0. So I'm going to start by taking the derivative. 12x cubed minus 12x squared. And I'm going to set that equal to 0. Okay, so remember when I said we didn't need to simplify derivatives because it wasn't important? Yeah, that's going to change. Okay. Now we're going to have to be able to simplify derivatives. The reason I need to simplify derivatives is because I want to be able to turn a function like this one from a difference, it's a subtraction problem, into a product. In other words, if I have two things that subtract and equal 0, that's not necessarily easy to solve. But if I have two things that are multiplied together to give me 0, that's easy to solve. Okay. Okay. Now this is fairly simple, and I chose an easy example to start. It's going to get a little bit nasty later on. Okay. Again, I turned a difference, a subtraction problem, into a product. Therefore, x is equal to 0 and x is equal to 1. These are what's called critical numbers. So if there is a max or a min, it could happen at 0 or 1. However, like the graphical example I did, it could also happen at the endpoints of the interval. So the absolute extrema is nice and easy to deal with because all you got to do now is check some points. And how am I going to organize that? I organized it into a graph. Or sorry, not a graph, a chart. This is from the interval. This is from the interval. And these two are critical numbers. And you need to test all of them. Okay? Those two came from there. The other two came from the previous slide. Once you get this chart together, then it's real simple. The biggest value is the absolute max. The smallest value is the absolute min. Okay, done. And the other points are just points. Who knows what they do? All we care about is the biggest and the smallest and an absolute max or min. Okay? Let's stop for a second and make sure everybody's with me. Are we good? Because we're going to change things up a little bit here. A lot of it, actually. Gents, we good?
Yep.
Okay. Beautiful. All right. We will do quite a bit of work with absolute maxes and mins. However, that's not the gist of this lesson. The big part about this lesson is something called a relative max or min. And a relative max or min takes a smaller piece of the graph and says, where's the highest point in this graph? Absolute maxes and mins. A function on an interval can only have one absolute max and only one absolute min. That's it. No exceptions. You can have a ton of relative max and mins. So if I look at this graph, this is another cubic. I've got some points highlighted in pink where there's a maximum value. I've got another area highlighted in pink that's a minimum value for that little pink window there. And you can create a whole bunch of different pink windows. So for instance, if I look at the sine graph, it goes something like this. It has an infinite number of relative maxima because every one of these is a peak, which would be a max. Every one of these is a valley, which would be a min. Again, one absolute max and min, a lot of relative maxes and mins. Question?
Aren't they all the same value though?
Not necessarily. Okay, so for instance, whoops, this guy. Coming back to this example again. There is no absolute max in this picture. However, there is a relative max right there. This is the absolute min. However, there are two relative mins. Okay, any low points become relative mins. Only one, the lowest point, is the absolute.
So do relative max mins only occur on the interval, whereas absolute occurs on the entire thing?
Yes, but the absolute maxes and min problems are usually given on an interval just to restrict the entire thing, to avoid things like this where it goes on forever and ever.
But the relative maxes and mins, wouldn't they still remain the same anyways? Because the function is like continuous, like sine of x is just
Yes.
a key.
Yeah,
So
but
then
it doesn't. That's not always true for every function. The
Oh.
sign, because the sign continues to repeat over and over again,
So
they would continue to be the
some are
same.
gonna go away.
Yep.
So-
Okay. If you understood the absolute max and mins, then the relative max and mins are very straightforward. We do the same thing. Okay, so we get rid of this mess. We're still going to take the derivative. We're still going to set it equal to 0. We're still going to solve. And all we care about right now, in this lesson in particular, is understanding the concept of extrema and how to find critical numbers. We'll talk later about whether or not those critical numbers are maximums or minimums. Actually, I'm pluralizing it wrong. It's maxima and minima. Just like absolute value or absolute max and mins, I commonly call them relative max and mins. However, some idiot also started calling them local max and mins. Again, I'm sorry. They're all the same thing. Okay? Now we need to talk about how that happens. So I have this example in here not necessarily because I don't think you understand it or that I want to beat a dead horse, but I wanted to do a little practice on taking a derivative. So if I know, and there's a picture down here in the corner, I know that this point is a relative maxima or maximum. You can see it in the graph. Therefore, if I take the derivative and I plug in 3, I should get 0. Or if I take the derivative and set it equal to 0, I should solve that and get 3. We can do that either way. And so I'm going to take a derivative. And many of you might attack this as a quotient rule. However, I'm going to suggest a different approach. And that is I'm going to do some algebra first. And do f of x is equal to 9x squared over x cubed minus 27 over x cubed, which means that 9 over x minus 27 over x cubed. I'm going to split the fraction first before I take the derivative. because I think it will be a little bit easier. Let's see. I forgot. This is 9x to the negative first minus 27x to the negative third. So I get negative 9x to the negative 2 plus 81x to the negative 4. And we can do this one of two ways. I could set it equal to 0 and solve, and I'll get 3. Or I can figure out what f prime of 3 is, which would be, let's see, it's 9, that's negative 1. And 3 to the 4th is 81, plus 1 equals 0. Good, it checks out. Most commonly, what we're going to do is take the derivative and set it equal to 0 and solve. But I wanted to show you that it also works if you know the point. You should get a slope of 0 because, again, if you draw your tangent line in there, from what we started with would give you that slope of 0. Okay, now let's talk about critical numbers. There's two things that we need to concern ourselves with. We've done this one already. However, this also happens. We will get a critical number in two cases, where the derivative equals 0 or where the derivative is undefined. Okay? So critical numbers come from f prime of x equal to 0 or f prime of x d and e.
So it always look like a sharp turn, like it's the end.
Yeah. Okay, now before I do this, let's talk about, let's go back to our discussion of dogs versus golden retrievers. Retrievers. Have we had this conversation? Have we talked about this before?
Yeah.
Yeah? Okay.
Yes.
All golden retrievers are dogs, but not all dogs are golden retrievers. Okay, good. The same thing happens with critical numbers versus, so critical numbers versus max or mins. All max and mins are critical numbers, but not all critical numbers are maxes and mins. Okay. So dogs are like critical numbers, golden retrievers are like maxes and mins, which is what these two things say. If you have a max or a min, it has to be a critical number, but not all critical numbers are maxes and mins. And like I said a while ago, we're going to focus mainly on finding critical numbers in this section. We'll deal with maxes and mins later. Go.
What are the other critical numbers? They're like, can be a critical number.
Oddities, weirdness, strange things,
Okay.
vertical asymptotes.
Okay.
That's part of what we're going to see is start looking at graphs and seeing, okay, wait, I got a critical number here, but it's not a max or a min. What's happening there? So
How do you define a critical number? Like I just like
critical number is defined as where the derivative equals 0 or where the derivative is undefined. That's it. Don't overthink it.
The restriction.
Okay, good? Zoomers, good? Okay, good?
Yeah.
Okay. All right, here we go. Now, this is an ugly problem. And the reason I gave you this ugly problem is because it's going to do a couple things. Number one, we're going to practice on how to find the critical numbers. But number two, that whole business about being able to simplify the derivative is going to become relevant here. Okay, so what I would like you to do is take the derivative of that function, set it equal to 0. Try to solve it. you might struggle with that. However, you should all be able to take the derivative. So it's 10:16. We'll come back at 21, and look at that derivative. And look at how to simplify that derivative to find the critical points, critical numbers. By the way, you should get 3 critical numbers. Okay, questions before I cut you loose? Good. Take a derivative, get up, take a break, go get a snack, walk around, get something to drink, and I'll see you in 5.
Starting to miss related rates all of a sudden.
Oh, don't say that out loud. If they hear you, somebody will hurt you if you say that.
Start to miss like, how do you do this addition from?
Exactly. Starting to miss
How do you
linear
do one
linear
and two?
equations. All right, let's go. Here we go. Let's see. Who are we going to pick on today? Prasant. Your group members asked if I would pick on you. Could you tell me what you got for a derivative, please?
The derivative I got to be.
Hold on, wait. Before you go any further, just give me your raw derivative. No simplifying, no nothing. Just your step 1 of your derivative.
So I did chain rule. So I did 2 times x plus 7 times 1.
Uh-huh.
Oh wait, do I have to do a product rule?
You
And
bet you
then add a
do.
chain rule?
Oh, yeah. You just realized that?
Yeah, no, mine is wrong then. Okay, I can just do it on the spot.
Oh,
You
okay.
do that.
Very nice.
The cube root of x minus 8
I'm gonna write it this way. Is that okay?
plus what is it, 1/3 times x minus 8, and then that's to the negative 2/3 power times x plus 7 to the second power.
Outstanding. Well done. Okay. So yes, it's a product rule. Yes, the cubic root of a function is to the 1/3 power, and I get that mess. Now there's a problem here, and the problem is that little plus sign. I have a sum, and I don't like a sum. Sums are difficult. I want it to be a product because then I can use the zero product rule. A times B equals 0. In order to turn this into a product, I'm going to factor out what they have in common. And this is why I picked this problem, because the factoring out gets a little ugly. All right, so I'm going to set it equal to 0. I'm looking at this as 2 different terms. I've got this term, and I've got this term. And the question is, what do those terms have in common? So I'm going to start with an x plus 7. And I have to decide what power am I going to factor out, because there's an x plus 7 in the first one, and there's x plus 7 squared in the second one. The rule is always take the smaller exponent, which seems silly now, but you'll understand why it's relevant in a second. Always take the smaller exponent. Well, since 1 is smaller, I'm going to take that out of there. Okay, easy. Now I've got x minus 8 to the power of either 1/3 or negative 2/3. Following the rule, I take the smaller exponent, which would be negative 2/3. Big honkin' bracket. If I look at the red term, what do I have left behind? Well, I have a 2 left. The x plus 7 got factored out. The x minus 8, and the question is to what power? Okay, so a little sidebar here. The reason why you take the more negative thing is the following. Let's suppose I have x to the 4th minus x cubed, and I factor that by taking out an x cubed. I think you all are smart enough to realize you'd get x minus 1. But why is it x minus 1? What you're actually doing is you're dividing. I'm dividing x to the 4th by x cubed, and I get x. I'm dividing x cubed by x cubed, which gives me 1. You all know that, but you probably don't think of it that way. You think of just factoring it out. Why is that relevant now? Because I'm factoring out an x to the negative 2/3. Whoops. I'm taking x minus 8 to the 1/3, and I'm dividing it by x minus 8 to the negative 2/3 because I took out the more negative exponent. 1/3 minus negative 2/3 is 1, which makes me happy because I don't have any ugly exponent up here. It's just x minus 8. Okay? Everybody good with that? That's why we take out the more negative exponent, because it leaves us with a nice pretty answer there. That's what's left behind in the red term. Plus, I got a 1/3 there. I got rid of the x minus 8 to the negative 2/3. That's outside. I took one of the x plus 7s. I left one behind. Go.
So for the x minus 8, I don't understand how like the negative 1/3 and then the negative 2/3 gets you.
I'm taking a negative or an x minus 8 to the 1/3, and I'm dividing it by negative 2/3. When you divide exponents, you subtract them. 1/3 minus negative 2/3 is 1/3 plus 2/3, which is 1.
Oh, okay.
And that's why we do that, because we get a nice pretty
It's
answer.
like when you multiply exponents, you add them.
Yep.
Okay.
This did exactly what I wanted it to. So now I have a zero product rule. I actually have A times B times C equals 0, but the same thing happens here. Okay, so where are my critical numbers? Well, x is equal to negative 7. That's one of them. That's from there. X is equal to 8. That comes from there. And then this mess inside the brackets, which would mean I'd have to do 2x minus 16 plus 1/3 x plus 7/3. And yes, you would have to solve something that ugly. Set that equal to 0 and solve. I will trust that in a calculus class you can all solve a linear equation, even if it has ugly fractions. It's okay. You'll be fine. I'm not going to do that because this isn't an Algebra 1 class. I will tell you that you get 41/7 as the other answer. Okay, so what does that mean? That means there's 3 critical numbers for this ugly function. Some of those critical numbers might be maxes or mins. We don't know. That's for a later lesson. Okay?
I'm so confused on how you simplified the first derivative.
How I got from here to here?
Yeah.
I factored out what they have in common.
What do they have?
So they have an x plus 7 in common, and they have an x minus 8 in common.
It's just because they're multiplied, so you can take one out.
Oh.
Yeah,
Oh, okay.
yeah. So you're just yanking out.
Okay. Good. Any questions from the Zoomers at home? I guess all the Zoomers would be at home. Well, I'm assuming, well, no, not all the Zoomers are at home. I'll just call you the Zoomers then. Okay, good. So, I think we're done here. Oh, yeah.
What? Maximum?
Anybody get the joke?
It's not maximum.
Bella, what's this picture on the left?
A family.
Yeah, and in a family, what's another term for the people in a family?
I'm not sure. I don't understand.
Bethany, do you get it? I see you
Is it
shaking your
relatives?
head. Explain it to us.
Isn't that an Extrema or something like that for Mercedes?
It's actually a Nissan.
It's a Nissan Maxima.
Oh, I'm just blind.
That's a Nissan Maxima. What's this?
Relatives.
Those are relatives. Get it? Relative Maxima.
Good one.
Relative.
Wait, what?
These are relatives, and this is a Nissan Maxima. So these are relative maxima. Get it? Get it? It's a calculus joke.
Oh, yeah. Instead of
Yeah, it doesn't get any better than this, kids. Okay, stop this. Here, go here, don't save, stop the recording.